Hello and welcome to this video on halogenoalkanes. This is a revision video for the AQA topic of halogenoalkanes. My name's Chris Harris and I'm from AlleryTutors.com, and basically in this video I'm just going to go through an overview of the topic and make sure that you've got basically a good insight as to what you expected to know in terms of content for the exam. You can the PowerPoints I'm going to use in this video, you can purchase. If you just click on the link in the description box below the video, you'll be able to get the PowerPoints from there, and then you can use them. You can print them out. You can use them as your notes. You can look back over them whenever you want. It's basically just to supplement your revision material that you may already have. So it might be a good idea to do that if you'd like them. Okay, right. So like I say, these are very specific to AQA. So we've got obviously the specification. We've got the spec points written down here. This just basically highlights the fact that anything in this PowerPoint is related to the specification. Okay, so naming halogenoalkanes. So halogenoalkanes are basically alkanes where they have one or more halogens attached to it. So in terms of naming, we have to find the longest carbon chain, and this will form the last part of the name. So this would be this is a bit like when you've got your alkanes as well. Then the names of the positions of the halogens of the molecules comes first. That's the prefix. And then we're going to use the prefixes fluoro, chloro, bromo, or iodo, and use the numbers to state their positions on the carbon chain. And you've got to make sure they're in alphabetical order as well. So if there's more than one halogen molecule, that's pretty important. And if you have more than one type of the more of the same type of the halogen, then you prefix with di for 2, tri for 3, and tetra for 4 of them. So let's have a look. Let's see what we've got. So we've got the first one here. This is obviously one carbon with 3 fluorines in there. So this is going to be tri. Again, I've highlighted in purple. So tri for the purple box. Fluoro, because we've got the fluorine there, and methane, because that's the longest carbon chain. There's only one carbon there. This one, as you can see, we've got 2, because we've got to say where the chlorine is. It's on the second carbon. Chloro, propane, 3 carbons long. And this one is a bit more complicated. Went a bit adventurous for this one. This one's going to be 1 bromo. Look, it's on the first carbon. 1 bromo, 1 dichloro, 2 chlorines, 2 iodoethane. Basically, I'm just trying to highlight the order, alphabetical order. B, then C, then I. Okay, so it must go in alphabetical order if you've got more than one type of halogen. Okay, so this one's 1 bromo, 1 dichloro, 2 iodoethane. Okay, try and say that one quickly. Okay, so that's basically the naming of the halogenoalkanes. Now we need to know a bit of properties about them. So we're going to look at boiling point trends of halogenoalkanes. Now boiling points of halogenoalkanes increase as we go down the group. And this is why. So the strength of the intermolecular forces govern the boiling points, how strong these things are. So basically the higher or the stronger the intermolecular force or bond, the higher the boiling point. And as we go down group 7, the number of electrons in the halogens, or the number of electrons in the halogen atoms, they effectively increase. So this means that you have more van der Waals forces, more energy is needed to overcome these strong forces, and this is why the boiling points of halogenoalkanes increase as we go down the group. This basically leads to, if we have all these as methyl, so halomethyl compounds, so we've got fluoromethane, chloromethane, bromomethane, iodoethane. So just to keep it the same, obviously the halogens are changing. So we're looking at the effect of the halogen. The halogen gets bigger, more van der Waals, boiling point increases as we go down the group. Bond polarity and nucleophiles, right? These are pretty important because we need to describe how these things react. So halogenoalkanes have a polar bond. They are attacked by nucleophiles. Okay, so we need to know what these little bits are. So halogens are electronegative. Okay, so here we've got chloromethane. They pull electrons towards themselves, and this is what leads to that polar bond that we were talking about. We put the delta negatives and delta positives on there. There's the delta negative and delta positive. It basically shows that the carbon is electron deficient, and your chlorine is electron rich. Okay, so the polar bond means that halogenoalkanes can be attacked by nucleophiles. Okay, so this is polar. So a nucleophile is just a substance that is an electron paired donor. So it donates electron donates electrons to the actual system. So examples of nucleophiles that you need to know are cyanide, ammonia, and hydroxide. So we've got them here. This one's your cyanide, there's your lone pair. Ammonia has got a lone pair, and hydroxide's actually got 2 lone pairs, but it doesn't really matter as long as you've got a lone pair of electrons. Notice don't have to be charged. Cyanide and hydroxide are, but ammonia isn't, but that doesn't matter. It's the lone pairs that count. Okay, curly arrows, you would have seen these before probably. They show the movement of electron pairs. They move from the lone pair on the delta positive, lone pair on the nucleophile, to the delta positive carbon. Look, lone pair, arrow going to the delta positive carbon. You'll see a lot of this in this topic later on. Okay, let's look at some very specific reactions. So reaction with hydroxide ions. So halogenoalkanes react with hydroxide ions via nucleophilic substitution. Okay, this is the name of the mechanism. If they ask about the name of it, this is what it's called. Okay, so the conditions for this reaction. We need warm aqueous sodium hydroxide, and basically this is going to give you the source of the OH- ions, which is your nucleophile. This is all carried out under reflux. So remember, reflux, we got the Liebig condenser on top of your round bottom flask, and you're heating it up. Water goes through the Liebig condenser, and it basically stops any volatile substances from escaping while you're heating it. Okay, so basically we've got your nucleophile. In this case, it's a hydroxide ion. This will attack the delta positive carbon and replace the hydrogen on the haloalkane and or halogenoalkane, and hence the reason why we say substitution, because we're swapping one for the other. Okay, let's start and write this mechanism out. So lone pair, okay, arrow goes to the delta positive carbon. So this is trying to form a bond with the carbon. Then, because this is now trying to form a bond with it, the carbon now has 1, 2, 3, 4, 5 bonds. So it needs to break one of the bonds. And it'll break the weakest one, which is always the carbon-halogen bond. So this one's going to break. And this is what we're saying here. So the CX bond, this bit, the X represents the halogen, breaks. Both the electrons move from the bond to the halogen, and a new bond is formed between the OH- and the carbon. So there it is. There's the bond that breaks. Okay, and we form this product. And you can see here, we have actually swapped the halogen now for an OH, because the OH has added itself on, the halogen's dropped off. So it's a nucleophilic, that's the nucleophile, substitution, because we've swapped it. Your chloride ion is now free to move around and do whatever it needs to do. Your alcohol is formed, and pretty much you can use that for whatever you want to use. Like for disinfectants and ethanol, as obviously you can be using alcoholic drinks, so that's ethanol. The overall reaction for this, RX, X is used quite a lot to represent a halogen. So this is your haloalkane, halogenoalkane, reacting with sodium hydroxide, forms your alcohol plus sodium halide. This would be a salt. That's it there. That's obviously just represent the halide ion. And the R bit represents the alkyl group as well. Okay, so that could be a CH3, and the halogen represents your bromine or chlorine. Right, mechanisms are really important. Make sure you know that we're going to get a lot of them here. So much so, here's another one. Right, so halogenoalkanes, they also, not only do they react with hydroxide ions, but they also react with cyanide ions. This time they're nitriles. So the conditions for this reaction, we've got warm, ethanolic, potassium cyanide. This basically is going to give you the source of cyanide ions. Again, this whole thing's under reflux. So we've got the nucleophile, again, same thing. There's your cyanide. Will attack the delta positive carbon and kick off the halogen. And we call this again substitution. So there's the first bit. Again, that bond breaks just like before, and we get a new bond that's formed between the carbon and the Cn-. There it is. And we form our product. There's our product. And this is called a nitrile. This one here. 1, 2, 3 carbons. Look, we've extended the carbon length chain. So this is propane nitrile. Okay. And so the overall reaction, again, there's your halogen, there's KCN, so this is potassium cyanide. React these two together, you form your nitrile, which is this, and your KX, your potassium halide. Remember your R's and X's, what they are. So this is called the nitrile. Okay, same mechanism, so it's not too bad. You don't have to remember a separate mechanism. Okay, right. Another one, right, this one's a little bit tricky. There's a little bit extra stuff in here, so you have to watch out for this one. Right, halogenoalkanes, on top of hydroxide ions and cyanides, they also react with ammonia via nucleophilic substitution. So it's a very similar start actually. This time though, we're going to heat it with ethanolic ammonia, okay, and we must have an excess of ammonia. I'll tell you why in a minute. When we see the mechanism, it's really important to have an excess. Right, let's have a look at the first bit. Here's our halogenoalkane. Here's our nucleophile. This is ammonia. Lone pair on here. And basically, this is going to, guess what? This is going to go to your delta positive carbon, and then it's going to kick off the halogen. Okay, so there it is. There's your first step. There's your second step. Okay, so same as before, except problem is that we've added on now a molecule which is now going to be quite unstable. The whole NH3 has added on to the carbon, and that's it there. There's the carbon, the whole lot's added on. But that's now left with the nitrogen with a positive charge because it's got 4 bonds. Remember, nitrogen can only bond 3 times. And we've got this chloride that we've kicked off. Now, this is where it gets a little bit different. Okay, so in the second phase, yes, we've got 2 phases of this. Another molecule of ammonia acts as a base by reacting with the hydrogen, and this is the reason why we need excess ammonia. So there is your ammonia, lone pair on the nitrogen, and what this is going to do, this is acting as a base here, and bases are proton acceptors. So this is going to go for a proton, not the nitrogen here. So there's the arrow. Look, we've formed the hydrogen, and then obviously because this is forming a bond with the hydrogen can only bond once. This bond has to break, and the electrons shuffle into that nitrogen there to stabilize it. So there it is. Okay, so we've stabilized that nitrogen, and all the electrons have moved in there. So the amine is produced. We can identify an amine by this kind of fishy smell, so it's very distinguishable. And the ammonium ion is also produced. This is NH4+, as you can see here. But we form an amine, which is this one here. Okay, so make sure you're able to identify this as an amine, and it can be formed via this mechanism. So we've got ammonia acting as a nucleophile here, because it's a lone pair donor. And we've also got ammonia, another molecule of ammonia, reacting as a base because it's going for a proton. It's a proton acceptor. Okay, so the overall reaction here, there's your haloalkane plus your ammonia, form your amine plus your ammonium chloride, which is just your salt at the end there. Alright, okay, so halogenoalkane reactivity. Okay, so halogenoalkanes, they become more reactive as we go down the group. Okay, so what determines this reactivity? The bond strength or the bond enthalpy determines the reactivity, not the bond polarity. Okay, and that's really important. Some people get this confused. Okay, so it's important that you get this right. So the table shows bond enthalpies of what are CX bonds or carbon halogen bonds. Okay, so the CI bond has the lowest bond enthalpy and is the easiest one to break. There it is. Okay. This means reactions with the CI bond will be more reactive. Okay, so remember this is to do with the enthalpy. So this is the weakest bond enthalpy. It's easiest to break. So in reactions won't take that much energy. So this is going to be much more reactive, the CI bond, than, for example, the CF bond, which is a bit stronger. Okay, so the reaction with hydroxide ions. So let's have a look at these. So halogenoalkanes react with hydroxide ions via elimination using ethanol solvent. Right, notice the reaction that we looked at before. This was the reaction of a halogenoalkane reacting with hydroxide ions, but this time we're using aqueous solvent back then, and we got an alcohol. This one would just change the solvent, same substance as a hydroxide ion, but we've changed the solvents. The solvent is now ethanol. So let's look at the conditions. Warm ethanolic sodium hydroxide. This gives you the source of the OH- ions, and this is carried out under reflux. Okay, and basically the main difference here is the OH- will attack the hydrogen ion, or the hydrogen, on a carbon adjacent to the carbon with the halogen on. Okay, and the OH- acts as a base, which is a proton acceptor forming water. Right, so what doesn't happen, we don't get, because this is dissolved in ethanol, we don't get the electrons moving in for the delta positive carbon. Instead, this is going to move in for a hydrogen that's adjacent to the carbon with the chlorine attached to it. So that could be this one or this one. So because this is dissolved in ethanol, so the solvent plays a really big role here. Okay, so this one's obviously going for the hydrogen at the top. It doesn't really matter which one. So this is going to go for the hydrogen. then the electrons in the bond move to form a double bond between the two carbons. So these electrons here jump in here and they form a double bond there. Now obviously because this is forming a double bond, we'll have this carbon will have too many bonds because it'll have 1, 2, 3, 4, 5. So it's got to break the weakest one. The weakest one here is the carbon halogen bond always. So the electrons will then jump from there onto the chlorine. There it is. Okay, so this is why that happens. And then the product is an alkene. So we've nicked this hydrogen with the nicked this hydrogen off the molecule. So the hydrogen's not there anymore. The chlorine's also been kicked off. So that's not there anymore. But we do have a double bond there. There it is. Okay, so we form an alkene. So this is your alkene. H plus and the Cl minus is eliminated. Obviously the H plus reacts with the OH minus to form water, and you get Cl minus as well. So the solvent is really, really important. And there's the overall reaction. So you've got your bromoalkane there. This is 2-bromo propane reacting with your potassium hydroxide, and this will form your alkene. This is ethene plus water plus potassium bromide in this case, or you can have potassium chloride if you want. Okay. So, is it elimination or substitution? So, like I say, the solvent plays an important role in deciding if a reaction is elimination or substitution. So, when we react sodium hydroxide with a halogenoalkane, we can make an alkene, which is the one we just seen before, using ethanol as a solvent, or we can use an alcohol, or we form an alcohol when we're using water as a solvent. But both alkene and alcohol with a mixture will provide a mixture of both solvents. So basically, if we had alkene and alcohol mixed, we'll get both of these substances formed. Okay, so let's have a look. This one here is your first one. There's your chloroalkane, your 2-chloropropane here. React it with OH minus or ethanol. The OH minus acts as a base because the solvent we're using is ethanol, and we form an alkene. Check out for EZ isomerism as well. There is a video where we looked at EZ in the introduction to organic chemistry. So have a look at that one there if you want to check out how you can spot for EZ isomerism, because you might get some EZ from that as well. And the other one, let's say now we're going to use OH minus, same OH, but we're going to use a water solvent. This time the OH minus acts as a nucleophile and we get a substitution reaction. So we form an alcohol instead. Okay, so really look out for the type of solvent you're using, because OH minus behaves differently depending on the solvent you're using. Okay, CFCs. So CFCs are basically chlorofluorocarbons. Now these are used, or were used, should I say, in refrigerants and propellants, in deodorants and things. So, but the problem is that these break down ozone in the atmosphere. So, and ozone is the layer which protects us from UV. So CFCs, these are molecules that have had all their hydrogens replaced by chlorine and fluorine. Okay, so they're pretty stable. That's why they were used as refrigerants. But they are broken down by UV if they're exposed to UV. So what happens is the carbon-chlorine bond, like this one here, is broken down by some UV that comes in. This is coming in from the atmosphere. And the radicals are formed, and these catalyze the breakdown of ozone. So you might have seen radicals before. So in the alkanes topic, for example, you might have seen radicals. So the CCl bonds are broken easiest. Okay, so these ones are easier to break than the CF bonds, okay, because they have the lowest bond entropy. Remember from the previous slide. So a CF bond is less likely to be broken because it is a stronger bond. So you just need to know that we form these radicals, and it's UV that breaks down these CFCs. And so now we need to know, well, how do these CFCs destroy the ozone? So we know how they're broken down. So basically they form these radicals, like we said, and these catalyze the breakdown of ozone. You need to know the little reactions for these as well. So here's the initiation step. Remember, obviously we've got the CFC, there it is. UV comes in, breaks the CCl bond. We produce two radicals, and eventually these will react with ozone. So let's have a look. So there it is, CCl3F plus H mu. This is basically just radiation energy. Then we form a radical. There you go, CCl2F dot plus Cl dot. So basically we've got a Cl dot and whatever the rest is. So we've got the two radicals there. Then obviously we've got a propagation step, and the Cl dot that was formed here reacts with ozone to form ClO dot intermediate and oxygen, and then that radical then reacts with more ozone to make oxygen and Cl dot. And basically, because this Cl dot is reformed, we know it's a catalyst. So let's have a look at the reaction. In the first propagation, we've got the chlorine radical that was formed here, now reacting with the ozone in the atmosphere. That forms oxygen, and you form ClO dot. Remember, the radical in step 1 is also the reactant in step 2, so we drag that down there. There it is. That reacts with even more ozone in the atmosphere, and that produces 2 molecules of oxygen, and you form your Cl dot. Remember, your radical produced in step 2 must be the reactant radical in step 1. Okay, so make sure they match. That kind of tells you how to work these things out. And because it's reformed, look, it was used there, and it's reformed here. That is a catalyst. That's how we know Cl dot is a catalyst. Okay, and termination, basically this is where we've got 2 radicals reacting together. So for example, we're forming Cl2, there it is, Cl dot plus Cl dot forms Cl2, and that's the termination step. So overall, what we have, and you can see them circled there in red and blue, we've got 2 molecules of ozone, which is the red one, producing 3 molecules of O2, which is the one in blue, and Cl dot is the catalyst here. Okay, so restricting use of CFCs. Okay, so CFCs are now banned because obviously the damage that they cause. So they're really stable and unreactive, and they're non-toxic. And like I said, they were used as refrigerants and propellants and deodorants. So it was demonstrated, though, by scientists that CFCs were damaging the ozone layer. So despite the advantages, the risks outweigh the benefits. Okay, and so obviously they're now banned. And remember, the ozone absorbs this harmful UV radiation from the sun, so it blocks some of the harmful types of UV, and it protects animals and plants, I suppose, living on the Earth. And obviously, if the ozone is depleted, we have lost that level of protection. So what do we use today? Well, now we use HFCs. These are hydrofluorocarbons. They're a little bit safer to use. And hydrocarbons also, just straight up hydrocarbons without any chlorine in it. So things like alkanes, etc., they could be used as alternatives. So they're a lot safer to use than what we used to use. And that's it. So that is a very quick overview of your halogenoalkanes topic. Again, just make sure you know your radical reactions and you know the mechanisms are so important here, especially the use of solvent with the hydroxide ion. That obviously is going to pose a little bit of a problem. If you're not too sure on the difference, just read the question really carefully. But like I say, these PowerPoints are available to purchase. Just click on the link in the description box below this video to get a hold of them. But that's it for now. Bye bye.